Oh, hello students. Welcome back to your last lab. Today we're going to be talking about interference and diffraction of light. The first thing we need to talk about when talking about interference and diffraction of light is the types of light sources we'll be working with. Now there's two main types that we'll be working with today. Coherent light sources, which you usually find in lasers, and incoherent light sources, which pretty much everything else is made up of. Coherent light sources have a wavelength that all of the light being emitted shares, and a velocity, which light in general tends to share when it's in the same medium, as well as a common phase, meaning that when you look at the light as a wave like this, all the troughs and peaks line up with one another so that there's no interference or diffraction going on normally. So lasers are designed specifically to create coherent light sources. Pretty much everything else that's not designed that way creates different types of light. So this light is made up of different wavelengths, which we would see as different colors, and different phases. So even if we have the same wavelength, which is what we see with the green wave here and the blue wave here, they're out of phase, they're exactly out of phase. So these two would interfere with one another, even though they're the same wavelength light and moving at the same velocity. And then, of course, we can have different wavelengths of light, and that's shown by the black wave here. So an incoherent light source is made up of different types of light moving at different phases, offset from one another by some difference, or with different colors. So now we can move on to destructive and constructive interference. And this basically just comes about when these waves interact with one another. So here we have two waves, one with a very long wavelength and one with a very short wavelength, that are superimposed in the same point in space. And when they do that, we get our two different types of interference. Constructive interference, where the peaks of the two waves add together to create an area with more intense light, or visible areas of light, where you can still see what's going on, and destructive areas where the troughs, or the low points of these two waves, would come together, and these areas appear in real life as dark spots between bright fringes in a interference pattern. Also, I'll mention that for all of our experiments today, we're using a laser that is at 650 nanometers. This is your standard red laser. So this is a coherent light source of 650 nanometers. Alright, so knowing what we know about how interference works with constructive and destructive waves and how we can form bright and dark fringes, we can set up an experiment, specifically the double slit experiment, where our laser light is coming in from the left here and interacting with a wall that has two slits cut in it. So these slits are here and here. They're a distance d apart. When the light goes through those slits, it spreads out and it continues on, and it will spread out in every direction on a wall some distance L away from the wall. But you will see that the light is not evenly distributed. There are certain bright spots shown by the dots here, with the brightest being in the middle, and then in between those bright spots are dark fringes. So how does this come about? Well, basically we have two waves of the exact same wavelength, and then we have a certain amount of length that they need to travel to get to the wall. This means that two waves hitting the same spot on the wall will be offset by some phase. That phase can be found geometrically, and if the phase is exactly one full period, it will be a constructive interference. If it's half a period, the peaks and troughs will align exactly, and these will cancel each other out, and we get a dark fringe. So you can do the trigonometry for every single point on this wall if you wanted, or you could use these simple equations. So what we're looking at here is the path difference, how much longer one of these is than the other one. So here A is longer than B, but you can find that very simply with this equation here. So d sine theta, where theta is the angle from one slit to the point we're looking at. And this angle is also reflected here if we were to draw a right angle off of the bottom line here up to where this slit is here. That would be the same angle that we're measuring there. So the angle between, lots of similar triangles going on, lots of trigonometry which you can play with in your own time if you wish. This can also simplify to m lambda. Basically, if you know the wavelength of your waves, all you need to know is the path length difference and how long each wavelength is, and then you can find out if you have a brighter or dark fringe there. And then m represents the number from the center of your brighter dark fringes. So the center fringe, the brightest one, is m equals 0. Going upwards, m equals 1, 2, 3. You can go until you can't observe any light anymore. And then downwards, negative 1, 2, and 3. In between these fringes are the half points, so those are your destructive interference. Those are your dark fringes. So m equals 1/2, positive or negative 1/2, 3/2, 5/2, and so forth. And then you can simplify that equation to here, where if you're looking for any one of these variables, you'll know d, you'll know the wavelength, and then you should know which fringe you're looking for. You can plug into this equation here and find either the angle or which fringe you would be finding. So that's the double slit experiment. You have two different slits where light can get through, and then the path length differences between these slits can tell you if you are getting bright or dark fringes. A similar experiment, but that works off a different principle, is the single slit experiment. So again, we have light coming in from the left. It is coherent light, all the same wavelength, hitting a wall, but this wall has a hole in it, and the hole is of width A. And there should be nothing here, but I've drawn in little dots to show that basically the empty space in the single slit experiment, in the slit itself, behaves as many, many slits. So each one of these slits creates its own waves and own path length differences. To visualize this one, it's in your handout, but to visualize it here, you can imagine that each individual dot is creating waves that propagate forward into space. So I've drawn them for the top and the bottom one. First, they are a wavelength apart, so from here to here is a wavelength, here to here is a wavelength, and where these propagate into space, the peaks, which is what I'm drawing here, where the peaks line up, you'll have constructive interference. So instead of just having your interference on a wall here, you have your interference into space at several different points. So I've circled the constructive interference points as the light propagates this way. So to visualize this one, it might be a bit harder, but imagine that you're in a pool or some very calm bit of water. You throw two rocks in and waves will propagate outwards. There will be peaks to the waves and troughs. Wherever the peaks of your two waves meet, so you throw in your rocks to different areas, eventually the peaks of those will meet, you'll get a splash, or an area where the water has a very high intensity. And that will be your bright fringes here. Also, the troughs will be meeting, and then you'll have an area that is deflected downwards more than the rest of the pond, and that would be your destructive areas, which would be in between these bright fringes. This again is the equation for that, where A is again the slit width, theta is from the center line to where you're looking for your fringe, m is the number of your fringe, and lambda is your wavelength. And then last, on to diffraction. Diffraction is basically the very, very similar idea, except that instead of using slits or something like that, we're using a medium that has some sort of pattern cut into it. So the thing we'll be working with in lab is a CD. CDs are basically just discs with lots of little grooves cut into it. So we've zoomed in to show kind of what these grooves look like. As the light shines on here, these grooves will reflect light, and then at some point there will be a wall over there. This is not drawn to scale, so this distance here between your diffraction grating and your wall should be many, many orders of magnitude bigger than the distance between your grooves. But to show things here, this is how it is. So just remember that L is much bigger than D. So what we have is each individual slit basically acts, or each individual groove acts as a slit and reflects light onto our wall. Again, we'll have bright and dark fringes, and we could measure from the center axis of this upwards. We could measure that as an angle from our slits or our diffraction grating, and we could also measure that as a height. So these should be heights instead of phi's. But when we have that, so these are phi's, these are angles, these are heights. When we do have that, we can basically go back to trace. So this equation here is similar to what we had in the last part, but this part here gives the relation between the angle, the distance between the grating and the wall, and the height, or how far apart these actually are. And then the interesting thing comes about when we're comparing two different dots. So the first dot and the second dot, the difference in height between them is delta H. We can simplify that down to this here, and we can get a good measure for how far apart our fringes should be. So if you want to change these things, there's a few things you could change. You could change the distance between your grooves. You could also change the distance to the wall. So in the experiment we're doing today, we'll probably be changing L, because we're usually given diffraction gratings of a certain distance. So we're going to be making L bigger. Making L bigger will make our delta H bigger, and that's how you can simplify some of the results for these.
Here's the setup for the single slit experiment. The laser is shining through a single slit of 0.04 millimeters. And after it shines through there, we get a pattern on the wall, again caused by the interference of the particle, of the light going through that slit. Next, we're going to change the slit to a bigger slit of 0.08 millimeters, and we'll see the difference in that as it shines onto the wall. Here we have the double slit experiment set up. Again, the laser is shining through our selection wheel. This time it's shining through two slits. They are both 0.04 millimeters wide and 0.5 millimeters apart from one another. The first thing we notice in the pattern is it does look quite similar to the 0.04 millimeter single slit, but if you look closely, you'll see some smaller dots, and that's because we're now using two slits. We'll change this wheel to the 0.08 millimeter slit size and 0.25 millimeter separation, and we'll see the difference in both the larger groupings of dots and what each individual dot looks like as we've changed these two variables. All right, so what we have here is a human hair taped in front of our laser, and that laser is placed a good distance away from the whiteboard, which we're projecting onto. And you can see the diffraction pattern coming off of that hair onto the board, and we're measuring that separation distance as well.
All right, so here we have our laser pointing at a holder with a CD on it. The light's pointed at the grooves of the CD and it reflects back in the direction it came from. And I'm tilting it just a bit so it doesn't hit the laser again. On the wall we can see the bright middle and then the first bright fringe above that. And as long as we know the distance from the CD to the wall and between these two fringes, we can get a good calculation for the groove separation distance.